For nearly a century, a cosmological cold case has remained wide open. We've known there's a silent operator lurking in the shadows of our universe, one that doesn't emit light or reflect it. It's a substance our telescopes simply can't see, despite the fact that it appears to outweigh all the familiar matter, the stuff of you and me, by more than 5 to 1. Physicists called it dark matter. It's fundamental to our models of the universe, and yet, we still don't have a clue what it is. For decades, it has been a cosmic phantom, detectable only through the gravitational pull it exerts on the stars and galaxies we can see. It's the ghost in the cosmic machine. But what if I told you that after all this time, we may have finally captured a glimpse of that ghost? What if, after 100 years of searching, we're finally starting to see its silhouette? Using some of the most powerful instruments ever conceived, we are beginning to map the hidden architecture of the cosmos, the gravitational scaffolding upon which everything we know is built. This isn't just the story of a mysterious substance, it's the story of how we're learning to see the unseen. Join me today as we probe this juicy new evidence and answer the question I know you're all thinking. Have we finally seen dark matter? Our story starts, as many do in cosmology, with a puzzle. Back in the 1930s, an astronomer by the name of Fritz Zwicky was studying the Coma cluster of galaxies, and he spotted something incredible. The galaxies within it were moving far too quickly. Based on all the visible matter he could account for, the cluster's gravity should have been far too weak to hold itself together. These galaxies should have ripped the cluster limb from limb long ago. How could what he was seeing with his very eyes be reconciled with the figures on the page? Zwicky concluded that something more must be at work, something dark, concealed from view, lurking within the cluster to anchor these galaxies in place. He called it Dunkel Materie, or dark matter. For decades, this idea was on the fringe. But then, in the 1970s, the astronomer Vera Rubin provided the most convincing proof yet. She studied the rotation of individual galaxies and found the same problem everywhere she looked. Stars on the outer edge were moving just as fast as stars near the center. This defied expectations. If the visible matter was all there was, the outer stars should have been moving much slower, like the outer planets in our solar system. The only way to explain this was if the entire galaxy was embedded in a massive, invisible halo of dark matter. Without it, our own Milky Way would fly apart. According to our best models of the cosmos, the familiar stuff, you, me, the Earth, all the stars, makes up only about 5% of the universe's total energy budget. Dark matter makes up a staggering 27%, with the rest being an even more mysterious force called dark energy. This means that of all the matter in the universe, about 85% of it is a complete ghost. It doesn't emit light, nor reflect it, and it doesn't even absorb light to cast a shadow, so it is truly invisible. So how do you see something that's fundamentally invisible? For a long time, we couldn't. We could only observe its ghostly effect on the objects that are visible to us. We knew it was the framework of the cosmos, the gravitational scaffolding that allowed the first stars and galaxies to form. But we could never see the framework itself. Until, perhaps, now. This is where things get truly revolutionary. To see dark matter, astronomers use one of the most brilliant concepts in modern physics: weak gravitational lensing. If another eccentric physicist by the name of Albert Einstein is coming to mind, you'd be correct. His theory of general relativity tells us that massive objects warp the very fabric of space-time, and light has to follow those curves. So, when light from a distant galaxy travels towards us, its path gets slightly bent by the gravity of whatever it passes, including immense, invisible clumps of dark matter. The effect is tiny, a subtle distortion in the shapes of background galaxies, like looking at the world through a slightly warped window. By meticulously measuring those tiny distortions across hundreds of thousands of galaxies, astronomers can work backward and create a map of all the mass causing the lensing, both visible and dark. This isn't science fiction. Using telescopes like the Hubble Space Telescope and the Subaru Telescope, scientists have already created breathtaking maps of this mass distribution. For the first time, we can see the intricate network of the cosmic web, not as a simulation, but as a structure measured from its gravitational effects. These maps reveal dense knots of dark matter where massive galaxy clusters live, all connected by long, wispy filaments. The visible galaxies are strung out along these invisible threads like beads on a string, confirming dark matter acts as the scaffold for the universe. And now, this field is being supercharged. With the incredible power of the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory, we are entering a new era. These observatories are designed to create even wider and more detailed maps, pushing this technique to its absolute limit. We're moving from a blurry picture to seeing the invisible in ever-sharpening detail. This isn't a direct photo of dark matter, of course. It remains invisible. But it's a map of its hiding places, drawn with the light of 1 million distant galaxies. Mapping where dark matter is a giant leap, but it doesn't tell us what it is. The leading theory today is that it's made of undiscovered particles, often called WIMPs, weakly interacting massive particles. No, we don't think they are particularly shy or cowardly creatures, but they have been highly successful in evading our detection. In many of the leading models, these hypothetical particles are their own antiparticles. When a particle meets its antiparticle, you might know, they cancel each other out and annihilate, releasing a signature burst of energy, often as high-energy gamma rays. This gives us another potential way to see dark matter, not through its gravity, but through the echoes of its own destruction. Like fingerprints left at a crime scene, gamma rays can tell us where the action is. For over a decade, the Fermi Gamma Ray Space Telescope has been scanning the sky, and it found something tantalizing. Emanating from the center of our Milky Way is a mysterious spherical glow of excess gamma rays. The energy and shape of this galactic center excess are remarkably consistent with some models of dark matter annihilation. However, like fingerprints, gamma rays can be left by many different sources, which creates a serious issue. The galactic center is a chaotic place, full of rapidly spinning neutron stars called pulsars that could also be producing these gamma rays. Distinguishing a true dark matter signal from that maelstrom is incredibly difficult. For years, the signal has been debated, but recent analyses have kept the dark matter hypothesis in the running. There is a catch, though. If this signal is from dark matter, we'd expect to see similar gamma ray signals from other places rich in dark matter, like nearby dwarf galaxies. For the most part, we haven't. This has led many to err on the side of caution. Still, the gamma ray excess remains a fascinating and unconfirmed clue. It's not definitive proof, but it is a persistent anomaly, a juicy lead that refuses to go away. So, to answer our question, have we actually seen dark matter? The answer is a beautiful, complex yes and no. We haven't seen a particle of it directly, that's for sure, but we are no longer completely in the dark. With gravitational lensing, we are now directly mapping its gravitational influence with stunning precision, revealing the vast, invisible skeleton that gives the universe its shape. And with telescopes like Fermi, we are picking up faint whispers of light from the galactic core that might just be the death cries of dark matter particles. These are two different kinds of seeing, closing in on the mystery from all sides. New observatories are coming online, brilliant human minds are on the case, and every new dataset is another piece of the puzzle. The era of dark matter being a complete ghost may be coming to an end. We are on the cusp of a dark revolution, and isn't it a thrill to watch it unfold?